Okay, where B is bending rigidity. Right? For the lymph wall, we don't have this. For the lymph wall, we have M, this one, right? Okay, what about the velocity continuity? Velocity in x direction has to be continuous. What is the velocity in x direction due to the plate? That is dy d eta dt, that is the velocity of plate at x equals 0. Okay? That is what? Minus j omega a exponential minus j omega t minus k b y. That is the velocity. What about the velocity on this side? That is simply pt over rho 1 c1, because that is the plane wave. Okay? And what I have? Exponential minus j omega t minus kt, that is k1. I have a two component in x and y direction. X component is cosine theta 1. Right? But I am evaluating this on x equals 0. So actually this term will go away. And I have k1 sine theta 1 y. In fact, what I have is I have exponential minus j omega t minus k1 sine theta 1 y. That's what I have. Okay? So this won't go away. So from this continuity, the one small thing but is important observation we can get is this one has to be same as this one. Right? So note that KB has to be equal to K1 sine theta 1. Wow. Right? Physical meaning is that the K1 sine theta 1 is the number of waves along y direction on x equals 0. That has to be same as the number of waves on the plate. That makes sense. Right? And also the velocity due to incident and reflected wave. What is it? That is, one thing is pi divided by rho 0 c0, and then something we can write, right? But the velocity in x direction should be, there's something cosine or sine has to be here, right? Cosine or sine? Cosine. So I will put over here cosine theta y. Is it correct? Divide by? Okay. So here I will put cosine theta 0. So what I can argue is that the transmission loss we will get is very much similar with what the transmission we have for the normal instance case. The only difference is partition impedance, right? The transmission loss is fluid loading impedance over partition impedance and fluid loading impedance. Therefore, the result is the same as we obtained in the previous case, because we are using same logic, assuming that there is an instant reflect and a transmission, there is a impedance discontinuity, and then apply the pressure velocity continuity on x equals 0. The only difference is this kind of things. So the result is the same. Only difference is the partition impedance and fluid loading, especially partition impedance, is different. Okay? But if the bending, if we are handling the frequency well above the resonant frequency, then we can use mass law again. What is the resonant frequency in this case? What is the resonant frequency in this case? Okay, when we have a partition, when we have this kind of partition, when we have instant, reflect, and transmitted, the resonant frequency, strictly speaking, undamped resonant frequency is simply S over M, right? But I am asking you, what is the resonant frequency in this case? Okay, that's interesting.